welcome to this second part of the course. Today we are going to discuss the concept of complex abelian varieties, which is the generalization of the construction that we saw initially for elliptic curves. On the very special thing that we saw that elliptic curves have is that it's not true for higher genus curves, is that they have this group structure on the set of points. And that's because, in fact, elliptic curves are the dimension 1 case of abelian varieties. This is the object that we will study in the second part of the course, and we will focus again on abelian varieties defined over complex numbers, because it's a more intuitive and hands-on example. So we start with the definition and some examples. So an abelian variety and now we are talking about the general definition. So over a field K is a complete connected algebraic variety A over a field K with maps M that goes from A times A to A, I from A to A, and an element E in the rational points of A, such that the structure defined on the set of points over the algebraic closure of K by the maps M and I is a group structure with identity E. So as I was saying, the first example of this that we have already seen is the case of elliptic curves. So yes, the first clear example is elliptic curve with point addition. In this case, the M map would be the addition of 2 points that we saw yesterday, the other day. I is the inverse, so just taking the 2 points that are in a line that goes through the point at infinity. One is the inverse of the other, or the opposite. And E is the distinct point that we chose for our elliptic curve, which in general is the point at infinity when we take a Weierstrass form. Another example that it's a natural extension of this is to consider the higher dimension variety that results from taking a product of elliptic curves. And with the addition that it's inherited from the point addition that we have originally. So we have defined the object, now we have to define the maps as is usual, and what we have is that a homomorphism of abelian varieties is a morphism that respects the group structure. So mainly, we don't really have anything new here. Is what we would expect. So a morphism between the set of points that respects the group structure. So it's, again, an example of this is what we saw yesterday with homomorphisms over elliptic curves. And among all those homomorphisms, those that will be of interest, of the most interest for us, is what are called isogenies. So let me explain what those are. Okay, that's hard to erase. Among those, we highlight isogenies. And what do I mean by that? Surjective morphisms between abelian varieties of equal dimension and in particular what we have with these is that the kernel of such a homomorphism is finite. And we define the degree of an isogeny is the degree as a morphism of varieties or what we would write as K of A over K of B, and we define this as the rank of the kernel. Okay, so again, this corresponds to what we already saw in the dimension 1 case, which is elliptic curves. And so the example that we inherit directly from there is the multiplication by M map. So let me write it in the general case of dimension G abelian varieties. So again, we have the same thing. We will write n in brackets that goes from the abelian variety to itself and takes a point P and maps it to n times the point P. And this is an isogeny of degree n to the 2g. If A is defined over K, then we have the following. If the characteristic of K doesn't divide n, the number we are multiplying by, then the kernel of n over the algebraic closure of K is isomorphic to Z mod n to the 2g, where g is the dimension of the abelian variety. This is actually an even only if, so let me write it like that. Otherwise, that means if the characteristic of K, that is P, divides n, we have that the kernel for P equal the characteristic of the field, the kernel of a power of P of the algebraic closure is isomorphic to Z mod P to the I Z to the power gamma, where gamma is a value between 0 and g, and we call it the P rank of A. Okay. So a related concept that we need for isogenies. Proposition. Let AB be abelian varieties of dimension G and let phi that goes from A to B be an isogeny of degree m. So what this result tells us is that there exists a unique isogeny phi that goes from in the other direction, so B to A of degree m to the 2g minus 1, such that m is equal to phi composed by psi, which is equal to psi composed by phi. here I'm doing a bit of an use of notation because on this side I'm referring to the multiplication by m on the abelian variety A, and here the multiplication by m on the abelian variety B. So it's not actually an isogeny, but let's accept the abuse of notation. And what this actually gives us is the following corollary. Being isogenous is an equivalence relation. So to refresh equivalent relations, you can try proving this. It's quite simple. The thing is that if we have that two abelian variety, that there exists an isogeny between A and B, then the isogeny from B to A, it's just the one we get from this proposition, and the rest of the results work nicely. And in particular, being isomorphic is the case of being isogenous with isogenies of degree 1. Okay, so this is again the introduction of the concept of abelian varieties in the more general setting. You will see a bit more detail on things like that in the second part of Stefano's course. But for now, for what we are trying to do here, we will focus on the case where the field of definition is the complex numbers. So that will be section 2. Let's go for it. So, as we already did with elliptic curves, now we do this extra assumption. We take abelian varieties that are defined over the complex numbers, and that allows us to work with an object that is much more comfortable for us. As you might expect from what we saw in dimension 1, this is going to be complex tori. So, it can be shown that over C, the set of complex points of the abelian variety is a connected, compact, complex Lie group. In particular, it is isomorphic to a complex torus. So we didn't see this when we talked about elliptic curves, but then let me now give you the formal definition of a complex torus. So let V be a complex vector space of dimension G, and let lambda in V be a full rank lattice. The quotient x of b by lambda is what we call a complex torus. It is an Abelian group with the addition in B. And now that we have what's happening with Abelian varieties when we consider them over the complex numbers, what we are going to do is revise all the objects and concepts that we have introduced so far, but in the case of complex numbers. Okay, so we will start again by a homomorphism. So now we let A, I'll try to stick with XY for toruses, AB for Abelian varieties, so that we can keep the settings separate. So X is the lattice B with B quotient lambda, X prime, it's B prime quotient lambda prime. And we take them of dimension G, G prime respectively. So now we have that a homomorphism that goes from one complex torus to the other is again a holomorphic map that goes from one space to the other and respects the group structure. And what that means in practice is that we have a homomorphism of complex vector spaces and let me give it different letters so that we don't confuse ourselves with one another. So capital F will be the homomorphism between V and V prime, and that it respects the group structure translates to the condition that the image by the homomorphism of complex vector spaces of the first lattice falls inside the second lattice. If you remember the example of the homomorphisms in the dimension 1 complex tori case, what we had was that it was just complex numbers, such that when you multiplied the lattice by that complex number, you felt inside the lattice of the second complex torus. And because we have this setting, we can actually consider the morphisms that we will call the analytic and the rational representation of a homomorphism that go from the homomorphisms of the complex torus to the homomorphisms of the vector spaces that send f, lowercase f, to capital F. That will be the analytic representation. And we will also have the rational representation that goes again from the homomorphisms of x prime to the homomorphisms with respect to the integers of lambda prime that send f to, and what do we have here? Well, we have the homomorphism of complex vector spaces, but just restricted to the lattice, which is what we want here. And here you can tensor by the rationals if you want to extend this, but some more details on this will again be given in the course by Stefano in a later lecture. And yeah, as I was saying, we call them respectively the analytic and rational representation of the homomorphisms of complex area. So right now we are just going through the concepts that we saw before. Later in this lecture, we will see that actually when we take bases of the spaces of V and lambda, then we can translate all of these directly into matrices, and that makes everything very tangible and clear. And we will see that in more detail in a moment. So as in with the Abelian varieties, a morphism between two complex story is an isogeny if it is surjective of finite index and if we recover the example of the multiplication by n, becomes very visual. In its description on complex story. And let me explain why with a drawing. You might remember this from when we looked into elliptic curves and the torsion, when we were talking about the Weierstrass points of an elliptic curve. So let me draw again a dimension 1 lattice. Remember that we usually took the first element of the basis to be 1, second element of the basis to be tau, and this gives us a parallelogram. Okay, looks quite good today. And so now multiplication by n, or the kernel of the multiplication by n map, are the points that when we multiply them by n become a point in the lattice. So for example, if we look at the kernel of multiplication by 3, it just means that we have to look at points that when you multiply them by 3, you end up in the lattice. So the easier ones will be 1/3 and 2/3, because when you multiply them by 3, you go to 1, which is a point in the lattice. The same happens with tau. You can take 1/3 of tau and 2/3 of tau, and this just gives you a grid of exactly 9 points, and I'm only taking these because when we take the ones on this line, we are already in the next copy of the cell, so we include these two lines and we don't include these other two because they are identified, and we get exactly that this is isomorphic to Z mod 3 Z to the G. Sorry, no. So 2G, which in this case is 2, and it's exactly these 9 points. In fact, we can write the kernel of n as just taking the homothetic lattice 1 over n lambda quotient out by the original lattice lambda. And that's exactly, this quotient is exactly these 9 points that we have drawn here. As you can see, the framing all of these concepts is much more explicit in the setting of complex story than it was on Abelian varieties. And it's, as I was saying before, it's especially helpful to take bases of the vector space and the lattice to make everything more explicit, which is what we are going to do next. So let me see if I can use the blackboard a bit more today. We have defined a complex torus as a quotient V quotient out by lambda. We take bases E1, EG in V, lambda 1, lambda 2G in lambda, and because lambda is inside V, we can actually write the elements we've taken of the basis of the lattice in terms of the basis we have chosen for the vector space. If we write lambda I in terms of the basis of V, then we obtain lambda sub I is equal to the sum for J equal 1 to G of lambda Ji E sub j. And if we write this in the shape of a matrix, we will get a G by 2G matrix over the complex numbers that will represent and determine exactly our complex torus. We obtain this, and we get the matrix lambda 1, 1, lambda G 1, lambda 2G 1 to G, lambda G to G, which, as I was saying, it's a matrix G rows to G columns with coefficients over the complex numbers. We call this matrix a big period matrix of X, and it is clear that it depends on our choice of basis originally. And it also determines the complex torus completely. Basically, this choice of basis, it's just an isomorphism from V quotient lambda to C to the G quotient big period matrix Z to the 2G. So one can ask what happens with the reverse, right? So which period matrices we can take so that this thing, this object that we have defined here, is actually a complex torus. And this is given just by the following proposition. Let pi be a matrix that is again G by 2G with complex entries. P is the period matrix, sorry, it's a period matrix because we have said that it's clearly dependent on the basis, so it's not unique. It's a period matrix of a complex torus if and only if the matrix that comes from taking as the first G rows the matrix pi, and as the next G rows the matrix pi complex conjugate, which is now a 2G by 2G complex matrix, is non-singular. Where, as I was saying, P bar is the complex conjugate of P. So the idea behind this proposition is exactly what you would think. You build this matrix, and the fact that it is non-degenerate, non-singular, means exactly that we have a vector space of dimension G and a lattice inside that is of full rank. You can try to write the details as an exercise. I will also write a reference in the right platform. And now that we have this matrix representation of a complex torus, we can again go back to every object that we have defined and redefine it in the shape of a matrix. And this is what makes the complex case very good for an introduction to this object, because it's linear algebra. It's something that we are very familiar with. So let me do that. We will start again by homomorphisms. So once more, let x bar be complex story of dimension g, g prime respectively. And now we take a period matrix for each of them. So suppose that pi, a matrix, and it has to have the right dimensions for the complex torus x. So g times 2g complex coefficients. And now for x prime, we got p prime, which is g prime times 2g prime complex entries are respectively period matrices for x prime. Now we take f that goes from x to x prime, a homomorphism. Then, okay, what's interesting now? So for a homomorphism of complex tori, we define the rational representation and the analytic representation, which was a homomorphism between the vector spaces or the lattices. But now that we have chosen a basis, the homomorphism between complex vector spaces, it's just a linear map. So a map that goes from C to G to C to G prime and can be represented by a matrix of the right dimensions. Let me write that. The analytic representation rho sub A of f is given with respect to the chosen basis as a matrix I'll call capital A, such that it's a G by G prime matrix. So the entry is the dimension of the domain, and G prime is the dimension of the codomain with complex coefficients. in the case of the rational representation, rho R of F is given with respect to the bases as, and now we have a matrix I'll call capital R, which is 2G times 2G prime with integer entries. And we had the condition that this representation had to respect the group structure, and in the case of matrices that becomes a very simple matrix equation, which is that A times the period matrix on the left give me a second to make sure that the dimensions work, the spaces work. Okay, this should work. I always, it's sometimes tricky to remember in which side goes everyone, but it's like this. So this is exactly the equivalent to the condition that we had, that the image by the analytic map of the lattice of the first torus had to fall inside the lattice of the second torus. And conversely, any two such matrices that satisfy this equation determine a homomorphism between the two complex tori. The other way? See, I always get it wrong. Yeah? Okay. Thanks. And just a final remark, I mean, this will work equivalently, like this translates exactly like this for isogenies. And the only one thing that is important to note is that for isogenies we had defined the degree of an isogeny. So if psi is an isogeny, then the degree of the isogeny is exactly the determinant of the rational representation of the isogeny. So now this concept that initially could be a bit confusing, it's something that it's very specific and explicit, because we just take a matrix with entries in the integers, we compute its determinant, and this tells us exactly the degree of the isogeny. And okay, we'll actually use this in a moment.